Let's jump right in with the SN1 reaction. In this case, we'll start with a simple molecule, a 4-carbon chain with bromine, reacting with something like H2SO4. Before we go into the mechanism, let's just look at what happens. The bromine, in this case, is going to be replaced with an OH group to give me an alcohol as my final product. This is for SN1. Now, if I want to do a quick overview of the SN2 reaction, well, I can start with the same exact molecule, 4 carbons, a bromine. I'll switch up the reagent slightly, where in this case, I'll use NaOH in a DMSO solvent. And for my product, I will get a 4-carbon chain with, wait a minute, an alcohol. Look at that. 2 different reactions, same exact starting molecule, same exact product in this situation. So what exactly are we looking at? And why do the reagents even matter? Meaning, what is the difference between the reagents I chose, given that we got the same exact thing? When it comes to substitution and elimination, SN1 by itself, SN2 by itself, simple enough, but put them all together, and this is the most difficult topic that you're going to see in Organic Chemistry 1, because most students try to memorize it. But if you get it, if you actually understand what's going on, then you can make this difficult topic something that you are confident in and something that you ace on your quiz and your exam. And if that is your goal, I want to see hearts in the comments, because today we are going to break it down to make sure that you really, really understand what's going on. Awesome. I see the hearts coming in. So let's back up all the way to the beginning. But first, for a copy of tonight's session notes, everything that you see me writing here, along with a substitution elimination worksheet that is not available on my website, just comment worksheet and I will respond with the link so you can download it and continue practicing. We'll start from the very beginning with breaking down the SN1 reaction. Yes, the letters and numbers actually do stand for something. The S stands for substitution, which I'll write as sub. The N stands for nucleophilic. So let's look at this first. When you see the word nucleophilic, it kind of sounds like nucleophile, which is exactly what we're looking at here. A nucleo, meaning nucleus, and phile, meaning loving, is a molecule that is nucleus loving. What is the charge of a nucleus? To help us understand the chemistry of what is going on here, the nucleus has a positive charge, and so a molecule that loves the nucleus, a molecule that loves a positive charge, has to be, well, negative or partially negative. So we'll write it as negative or partially negative. And this is the key behind understanding the reactivity that's going to happen. So make sure you pay attention to charges, partial charges, and overall chemistry. The 1 in SN1 tends to confuse students a lot. It's not a one-step reaction. In fact, it's the opposite. That 1 stands for unimolecular, where uni does mean 1, but specifically it tells us 1 at a time. 1 step at a time in a multi-step reaction, where this reaction can keep going and going for quite a few steps. So let's look at the mechanism for how this reaction happens, and then we'll look at more difficult problems after. We'll start with just the very simple reaction that I already showed you, where I have a starting molecule with a leaving group attached. In this case, the leaving group is bromine. Bromine, as a highly electronegative atom, even though it's very happy with the covalent bond going on here, it's bound to carbon, it's neutral, everything is fine. Because it's so electronegative, it's pulling and pulling and pulling on that electron density until eventually it just breaks off. It is pulling so hard that it pops off. And that gives me the intermediate in this reaction, where bromine is just wandering somewhere in solution, completely surrounded by the solvent molecules, and we're left with a carbocation intermediate. Now, let's quickly go back to the reaction that I showed you so we can pay attention to the solvent. In this case, I gave you H2SO4 and H2O. Typically, you have your reagent, the thing that's attacking written at the top, and the solvent at the bottom. But here, that's not the case. H2SO4 does not fit the criteria of what we discussed here for being nucleus loving, because it has to be negative or partially negative. And H2SO4, where did my reaction go? Here we go. H2SO4 is an acid. An acid is a proton donor in solution. Anytime you see a strong acid like H2SO4, that is not what's reacting. That is just a source of protons, of acid catalyst in solution. And you have to look at what else is there. In this case, we have H2O. The solvent is going to stabilize the protons in solution. It's also going to stabilize that Br minus, never to be heard from again, just stabilized as a spectator ion somewhere in solution. And so if bromine is completely surrounded by the partially positive hydrogens in water, something else is going to be attracted to that carbocation. In this case, it's the water molecule itself, specifically the partially negative electrons on oxygen, because these are highly, highly electronegative, highly, highly polar. If you think about what happens in the polarity of a water molecule, oxygen pulls electron density, gets really, really partially negative, and attacks the carbocation. When that happens, well, first we have to show the next intermediate. And in this case, I have the new bond where the oxygen attacked, oxygen, 2 hydrogens, now only 1 lone pair and a positive charge. Technically, this is where my reaction is done, but we don't want to have a charged product. You want to have a neutral product. And the way you show that is very simple. Bring another of your millions and millions of water molecules that are in solution, because that's my solvent. Grab the hydrogen to deprotonate, and that gives me my actual final product, which is now just an oxygen, 1 hydrogen, the lone pair that it had before, and now this bond here breaking, well, technically that's the bond right there, as a second lone pair, a neutral alcohol as my final product. Some professors want you to show everything. Let me know in the comments if your professor wants to see all the side products and all the spectators and all the balanced things. And if that's the case, you would also show your H3O plus, which is the water molecule, the extra hydrogen that got grabbed, countered by a Br minus. Notice that this balances out, a plus and a minus that's neutral, and just kind of floats around somewhere in solution. If you're with me so far on this mechanism and the overview of the SN1 reaction, let me see thumbs up in the comments. If you have any questions, go ahead and type it in. I know there's a delay from when I ask you a question until you hear me and type it in, so I will go back as needed, but I want to make sure that you're with me first before we jump in even more. A couple of rules for the SN1 reaction before we continue. Because this has a carbocation intermediate, there's a couple of things we can get out of here. First of all, notice that was 1 step, 2 step, 3 step. The SN1, the 1 was 1 molecule at a time. This one reacted. The nucleophile did not come in until the carbocation formed. So we had 1 step and another step and another step. Now, even though we're saying that the secondary carbocation formed, and we know that carbocations are kind of stable or stable enough, the thing is, a carbocation is stable enough compared to, say, a primary or a methyl carbocation, but it's not a very stable, not a very ideal molecule. And that means anytime you have a carbocation intermediate, you know that this is a slow reaction. A very, very slow reaction where the rate determining step, the slow step, is the carbocation formation. So that would be this right here. as the slow step. And let me see, I saw a question come in. Was H2SO4 ignored? No. And that is a very, very good question. What happened to H2SO4? It dissociated in solution. Anytime you have a strong acid in water, the acid will dissociate, you get your protons, and then somewhere off in solution, we have an HSO4 minus. Before we even put in our starting molecule, as soon as you put an acid catalyst, immediate dissociation. Question. Why Br minus didn't abstract an H plus? Very, very good question. If we have a negative, why does it not grab a positive? Two reasons here. One, bromide is a very weak base. It is a big halogen or halide, electron density all around, distributed, well carried, very stable, and that makes her a very poor base. Weak bases are not very reactive, and so it's not strong enough to grab a proton. But also, even if it were strong enough to maybe not grab a proton, but maybe attack the carbocation, it is completely surrounded by water. It is caged. So imagine that you have a family, either your own children or your nieces or nephews or your friends' kids, and you go to play and they love you and they play with you and you say you have to go. And now all the kids crowd around you and they give you hugs and they cling for dear life. Don't leave, don't go. Not really going anywhere. I'm just picturing my toddler when sometimes he doesn't want to go to daycare. He'll just cling to me and say, I stay home and play with mommy. And that kid has a strong grip for an almost 3-year-old. So that's what's happening to bromine, completely caged and not able to do anything. What is done with the leftover Br minus and OH3 plus? These are just floating around in solution, just minding their own business, hanging out. I think I saw a couple more questions. Because the chat is scrolling, I'm going to ask you to type your questions again. Will this also follow me in ethers, epoxides? Aaliyah, absolutely yes. So the Williamson ether synthesis is a glorified SN2 reaction. If you need to create an ether, this is one way to do it, SN1 or SN2. So definitely, definitely pay attention to those as well. And I love that you made that connection. So going back to this. The SN1, because of the carbocation intermediate, is a slow reaction. And I'm going to put a note for you. Key carbocation intermediate. Note this, memorize this. Do not ever give me a carbocation for SN2, only for SN1, because that is the rate determining step here. And if you are asked to memorize or calculate the rate, the equation is very simple. The rate of an SN1 reaction is equal to some constant K times, I don't know why I did that, times the concentration of the alkyl halide. The more alkyl halide that I have, the carbon holding the leaving group, the more product I will get, the faster the reaction. This is technically where that SN1 comes from, that one right there, because there's only one thing in the rate expression, in the equation for the rate of this reaction. Now, when it comes to an SN1 reaction, even though we know the general mechanism and we know that it's a slow reaction, what's the word for it? How slow it is will change depending on what we're looking at. I gave you a starting molecule that looked like this with a bromine. And we know that a carbocation at the secondary position can form, and it's, well, we can call it stable enough. But if I have a starting molecule that looks like this, which is very, very similar, except now bromine is sitting at a tertiary position, would you expect this to be faster or slower than the bromine sitting at the secondary position? Well, what does the intermediate look like? And this reaction continues, so I didn't show you the rest. When the bromine leaves, and it doesn't just have to be bromine happens to be what I chose to show you here, we get a carbocation, and this time it's a tertiary carbocation, which is a lot more stable. And here's the thing. The more stable the intermediate, the more likely the intermediate wants to form. The less stable the intermediate, the more likely the intermediate will fight not to form and slow down the reaction. If you look in the video description, you'll see a link to my carbocation stability tutorial, and I go through this in a lot more detail. And so if you need a review on carbocation stability, carbocations with resonance, carbocation with benzene rings, all of that is covered. The key here is the more stable the carbocation, the faster the reaction is going to be. And I see quite a few correct answers coming in. Absolutely. A question came up that hinted at stereochemistry. It was an SN2 question, but I'm going to focus on the concept of it here. The stereochemistry of an SN1 reaction is going to be what? Well, first we have to ask, will there be stereochemistry? For example, if I have a molecule that looks like this, with a chlorine as my leaving group, and I reacted in a solution of H2SO4 and CH3OH, methanol. In this case, the mechanism is going to work exactly as we showed before. Chlorine will leave. I get a carbocation intermediate. That carbocation is going to look like this right here. And then in the next step, my alcohol, my solvent, is going to attack CH3OH like that. I didn't mention this before, so let me point it out here. This is called a solvolysis reaction. Solvolysis means if the solvent is the reactant, because remember H2SO4 we said is just an acid catalyst. If the solvent is your attacker, the solvent lyses. It breaks and reacts. This is a solvolysis reaction. We don't have a separate attacker. The CH3OH is going to attack. We get questionable stereochemistry here, giving me an OCH3 with another H, one lone pair positive charge, and in the last step, I deprotonate. What happens to the stereochemistry of this reaction, where my final product, Aaliyah, an ether, very, very important to keep in mind. So there's two ways to answer this question. This one in particular is actually a trick question. This chlorine has no business being on wedge because there is symmetry going down the molecule. And because there is symmetry on the molecule, the product, both the starting molecule and the product, are achiral. There is no stereochemistry here to begin with. If, however, I give you a different molecule, so for example, we'll start with this ring. We'll put a methyl group on here. We'll put a chlorine here. Now I most definitely, let's move the methyl group here. No, actually that wouldn't work. It has to stay here. Now I do have a chiral molecule. In fact, I have a chiral center here and a chiral center here. If I choose to react it with the same reagents, H2SO4 in CH3OH, I see a question. How do we know it's the CH3 going to attack and not the H2SO4? This is such a good question, and that's why I'm answering it multiple times, because professors somehow don't seem to convey this enough. H2SO4 is not a nucleophile. SN1 nucleophilic substitution, we need a nucleophile to attack. And a nucleophile, as we said earlier, is negative or partially negative. H2SO4 is an acid catalyst, and it is only here to give you protons in solution. It doesn't react. It doesn't do anything. Just protons in solution. It's a positive molecule. Once the H plus comes off, the HSO4 minus is so stable and so weak that it doesn't react. The only thing that we're left with, the most nucleophilic, the most negative thing in solution, is typically the thing with the oxygen or the nitrogen. Not the oxygen in here, because that has resonance. It's your water, your alcohols, your amines, or anything along that line, along the nature of having a polar group in there with a negative. That is going to be our attacker. So we see this right here. We cross out the H2SO4 because it's only a source of H plus in solution. Once again, we know that it's CH3OH going to attack. And if you look in the description, I have the backpack trick linked, which is how you know that you simply drop that the H off and for my product here, let me show you a shortcut for how to come up with a product. Because you don't want to go through the mechanism every time. In fact, let me see hearts in the comments if you want to know a very quick and definite way to get the right answer without having to draw the mechanism each time if your professor is not asking for it. And I see the hearts coming in, so here's the shortcut. First, redraw your skeleton exactly as you see it, meaning all the carbons on there. That is this right here. Because this is a nucleophilic substitution, the nucleophile is going to substitute, specifically the leaving group. Find your leaving group, cross it out, and in place of the leaving group, use the backpack trick to put it right there. The incoming nucleophile goes right there. And the question is on stereochemistry, so I'm just going to draw it on a squiggly right now because we're not yet talking dash or wedge, and put the OCH3. So again, the trick, redraw your skeleton as you see it. So 1, skeleton. 2, cross out your leaving group. And 3 is your nucleophile in the same spot as where your leaving group left. And that gives me the OCH3. So now I know how to find the answer without the mechanism. And the product is chiral, or rather has stereochemistry, because this is a chiral carbon and this will be a chiral carbon regardless. So the question is, do I put it on a dash or a wedge? And how do I know to do that? What determines if it's going to be dash or wedge in an SN1 reaction? Question, will you only have one solvolysis and H+, or can there be more than one of each? Typically, you're given one acid catalyst, in this case, H2SO4, could have been HNO3, any acid catalyst. And sometimes I've seen a professor do a reaction where you have water and alcohol mixed together, but typically it's just one. That's going to be an SN2. We'll come back to that. We're not looking at elimination today, but I do plan to cover that in an upcoming session. So you're just replacing or substituting, not for solvolysis, we're substituting for the SN reaction. For SN1 and SN2, it is a nucleophilic substitution. The nucleophile substitutes. And so what about chirality? Matthew, you are absolutely correct. There will be 2 products. Remember that the intermediate for an SN1 reaction is a carbocation. What is the hybridization and therefore the geometry of a carbocation? A carbocation is sp2 hybridized. sp2 is trigonal planar, aka flat. And that means the incoming nucleophile can attack from the top or from the bottom. It can attack from both. And so the product is going to be racemic, where 50% of your nucleophile chiral positions will be R and 50% will be S. And in this case, your professor may also ask you the relationship between the 2 molecules. If I have one that is R and the other one that is S, what is the relationship between these 2 molecules? And let's put this one, let's make this one smaller because it's an intermediate. So we'll make this one with a wedge. And this is a trick question that not only do many students get wrong, but I have seen answer keys from exams that professors have released with the wrong answer. What is the relationship between these 2 molecules? They are not enantiomers. They are not enantiomers because even though these 2 appear to be enantiomers, these 2 are still the same. And if you have 2 chiral centers on your molecule where one is the same and one is different, they are diastereomers to each other. Diastereomers, one is the same and one is different, and we get about 50-50. So there's no inversion, there's no retention. Well, technically it's 50% inversion, 50% retention, but that's not the way you answer this question. You answer this question by saying it's racemic in that the nucleophile can attack from both the top and the bottom. So this is 2 products for an SN1 reaction specifically. So they are racemic, yes. And racemic simply means that we have, I think of it as a race between R, and S, in that we have both. I think that covers the basics for an SN1 reaction. So let's jump on over to SN2. And what I want you to pay attention, remember the opening reaction where I showed you the same starting molecule, the same product? I want you to pay attention to the similarities and the differences. And as I'm going through this, don't worry about writing everything down. For a copy of my session notes from tonight, along with a practice worksheet that is not available on my website, just put worksheet in the comments and I will link it to you after. For the SN2 reaction, what do we have? The S, once again, stands for substitution. The N, nucleophilic, so far, just like we saw in SN1. The difference here is that 2, where the 2 stands for bimolecular, and the bi tells us how many molecules are reacting at a time. 2 molecules are reacting at the same time. It's not one does a thing and then the other one does a thing. No, they bump into each other and they react together. So what we're doing, as a reminder with the shortcut, the substitution just means a swap. And what specifically am I swapping? The nucleophile for the leaving group. So let's see what that looks like in a mechanism. We'll use something, well, we'll use the same molecule I had at the start, where I'll give you a bromine as the leaving group. And what did I use over here? NaOH and DMSO. So let's use the same thing again. NaOH is not a neutral molecule. Don't forget, anytime you see Na plus, K plus, or anything like that, or I meant to say Na or K, that's just a positive spectator. It's just there to balance charge and it does nothing in the reaction itself, meaning the Na plus just wanders off somewhere in solution and OH minus is what's left as my attacker, as my nucleophile. Remember we said that nucleophile means that it's nucleus loving and something negative or partially negative. In this case, it's a full-on negative. Now the OH minus wants to come in and attack. Well, why does it want to come in and attack if I have no carbocation? Very simple. Remember with the SN1 reaction, we said bromine is highly electronegative and it's pulling and pulling and pulling on those electrons until eventually it breaks off. But that takes a long, long time. OH minus is a strong molecule or strong ion. It's negative. It has a charge. It's a bully. It is not going to wait around until bromine eventually manages to pop off the molecule. It is going to attack way sooner. So when bromine is pulling and pulling and pulling, the carbon here is left very partially positive. And that is where the OH minus is attracted. It wants to attack from the top, if that's where it happens to land. But bromine is in the way. It can't get there. So it has to come from the other side. It has to come from the opposite direction. This concept is called a backside attack. And when it does that, when it attacks from the other side, bromine, which is already pulling on that electron density between the carbon and bromine, breaks off. It gets kicked out. And what that leaves you with is an oxygen that is now attached opposite where the bromine left. So if bromine was on a wedge, the OH is on dashes. We don't have two options. We have one option, opposite what I started with. Bromine coming forward, OH minus is now going back. And this is a chiral molecule. If I did it with an achiral starting molecule, it wouldn't matter. Meaning if my starting molecule looked like that, that's not chiral. And so the product wouldn't be chiral either. But in this case, it is. And I only have one option for the product. And that option is an inversion of configuration or an inversion of the stereochemistry. So I get the opposite stereochemistry of what I started with. And let's prove that real quick. That would be 1, 2, 3. The starting molecule is R. And for the product, I have 1, 2, 3. But the invisible hydrogen number 4 is coming forward. So I have to flip it. 1, 2, 3 goes that way. And it's S. R becomes S because of the backside attack. Right, I see some questions. Data entry. Mechanisms. So the SN1, SN2, E1, E2 mechanisms apply to reactions involving epoxides and sulfones. Yes, an epoxide is one type of. So epoxides typically get opened with substitution rather than elimination, but it's like an SN1 and SN2. So the acid catalyzed will be like the SN1, the base catalyzed will be like SN2. But a lot of your sulfur reactions, a lot of your ether reactions, they're just glorified SN1 and SN2. And so what I'm showing you today is going to be relevant to those molecules. You're just limited in the kind of molecules that you're working on. Why is OH? It's not wedged, it's dashed. OH is dashed because it had to attack from the other direction. So if you imagine that bromine is facing this way, OH can't come in from there because it's blocking. It has to kind of sneak around from the back and kick it out. So if I have a molecule, let's see. Oh, my son managed to leave me with some of the kit. He thinks it's a toy. He likes to play with it. So if I have a molecule like this, and he likes these. So these are the ones that he tends to take. Let me see if I can make that full screen. So if I have a molecule like this, and that's my bromine, I can't have a nucleophile coming in from here because it's being blocked. I can't reach there. So it has to come in from the other direction, from here, and kick that out in the process. But it came in from here, so it's attached in the opposite side. That's called an inversion of configuration, and it will give you the opposite chirality. If there are any other questions on this, go ahead and type it in. Otherwise, we'll continue. I know there's a delay, so just type your questions. Even if you're watching the recording, type it whenever you hear, whenever you think of a question, and I try to come back to the comments after the fact all the time. In this reaction, there's a couple of things that we have to recognize. First, how is this reaction different? Well, there's two things. One, we talked about the OH minus. And so the first difference we want to look at between the SN1 and SN2, let's put that here, SN1 versus SN2, but actually I'm not ready to talk about the differences because we're still talking about the SN2 reaction. The SN2 reaction, key, absolute key, please, 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 if you take nothing out of today's session, know this. There is no carbocation intermediate. Because we're dealing with a strong attacker, this attacker is so strong and so fast, it does not have time to wait around. It does not wait for a carbocation to form. It does a quick attack and kicks out the leaving group. And that means this is a fast reaction. Carbocations are slow. Strong nucleophiles are fast reaction. Strong NU for nucleophile. In fact, the rate of an SN2 reaction is equal to some constant K, specific to each individual reaction, times the alkyl halide, meaning the carbon holding the leaving group, times the nucleophile. Because we're looking at two different things, that is where that 2 comes from in SN2, a bimolecular reaction, because it's looking at both the concentration of the alkyl halide and the concentration of the nucleophile. And just like the SN1, we have general rates, but the speed can change depending on what we have. If you think about, let's go back to the model kit. If you think about what I had here, and now imagine that I still have the red leaving group like I showed you before, but it's on a big bulky molecule. Whoops. It's on a big bulky molecule right now. If a nucleophile wants to come in and attack, it can still come from the top, but it has a lot more to get through. There's so many things in the way that it won't get there as quickly. If it happens to come from here, and then it's got to go this way specifically, but it can't just approach it the way it did before. So what this means is if you're looking at a molecule with the leaving group, look at where the leaving group is located. If there are other groups around it, meaning big bulky things, they will slow down the reaction, and that means they will not allow this thing to happen as quickly. Okay, so what does that actually look like in terms of something you can take away in your notes? If I have a leaving group sitting on a methyl, that is a tiny little carbon with 3 hydrogens and a leaving group, so easy to approach from any direction. That will be the fastest reaction for an SN2. If I put one other carbon on it and I make it primary, meaning I have a leaving group right there, so we'll put it like this. A primary leaving group is still pretty accessible because it can approach it from a couple of different directions and do a backside attack. If the leaving group is sitting on a secondary carbon, it's now starting to slow down. And if that leaving group is on a tertiary carbon, there is no way for the nucleophile to get in there. This reaction will not happen. You have no SN2 for a tertiary leaving group because there is too much steric hindrance. There is no way for it to get in there. And so typically you want something like a methyl or a primary leaving group, and then you're good to go. Another question I caught about the solvent. Eddie, perfect timing. Okay, right here. Is there any need for the DMSO? That is a very good question. Notice that I gave you DMSO here, and yes, that is really, really important. SN2 reactions will typically have a polar aprotic solvent. The idea with a polar aprotic solvent, as opposed to the polar protic solvent, which we kind of talked about but didn't name for the SN1 reaction, is that the polar aprotic solvent does not have hydrogen bonding, and therefore the polarity difference in the solvent is not enough to stabilize any sort of carbocation intermediates. The polar aprotic solvents that you should memorize for this class are DMSO. If you're taking the ACS exam, let me know, put ACS in the comments. DMSO is dimethyl sulfoxide. ACS students, you have to know all these structures. DMF is another common one, dimethyl formamide. Acetone is just a small ketone. THF is a common ether, but in general, ethers will do. And acetonitrile is another one. Although I am out of room. Yep. And let me draw them for you real quick so that you can see what we're specifically dealing with. DMSO is dimethyl sulfoxide. That means I have 2 methyl groups. Notice not a single hydrogen is on oxygen or nitrogen, so there's no polarity difference between hydrogen and what's holding it. DMF is dimethyl formamide, so we'll start with the formamide, and then, oops, I need the nitrogen, right, because it's an amide. Dimethyl is 2 CH3s on it. Acetone is just a small ketone. THF is tetrahydrofuran, it's just a cyclic ether. And acetonitrile is an acetonitrile, like that. So all of these have some polarity with that oxygen or the nitrogen, but no protic hydrogens, no hydrogens capable of hydrogen bonding, meaning they are very bad at stabilizing a positive charge. But what they do is if there's a negative in solution, for example, my OH minus, the polar aprotic solvent will make that negative almost like make it angry. It pokes it, makes it really, really aggressive, and therefore makes it more reactive. If I didn't have the polar aprotic solvent, I'd be leaning towards an E2 reaction potentially. Not a topic for today, but the solvent is a key differentiator between the SN2 and the E2. And it looks like quite a few students are taking the ACS, so you have to know this. Hi, Trader, Gina, Tess, Alicia, Natalie. Yes, you will have to know these structures, so know their name, know how to draw them, or rather, know how to recognize them. So now, let's jump on over to the difference between SN1 and SN2. The shortcut for how to do the reaction is exactly the same. So if I have something with an OH, and I'm trying to come up with a product. Remember the shortcut, redraw your carbon chain, get rid of your leaving group, put your nucleophile. None of that changed. It's really a question of everything else that is a difference on the molecule. So the different ways to tell them apart. The first thing I look at is the alkyl chain. The alkyl halide, specifically the carbon holding the leaving group, you want to ask the question of, can it form a carbocation or a stable carbocation? With an SN1 reaction, if I have a methyl leaving group, I can't form a carbocation, I can't do a SN1 reaction. And then if I'm looking at an SN2, is it hindered? Because remember, an SN2 cannot attack at the tertiary position, as we already saw. The second thing I look at is the attacker. So we kind of hinted at this. Let's take a look at this in a little bit more detail. The attacker is the incoming nucleophile, and that is the molecule that is going to attack. And really what I'm looking at is strong versus weak. What makes a molecule weak? What makes a molecule strong? These are just atoms and electrons. How do we define them as strong versus weak? What we're really looking at here is the strength in terms of stability. So shockingly good? Your answer is not shockingly good. It is excellent. The strength is determined by how stable the molecule is, and the stability is often determined by charge. So what does that mean? Charge is a burden. Molecules do not like holding charge, and if they have a charge, they want to get rid of it. So if I have a molecule that is charged, that is unstable, and it wants to attack. And if it wants to attack, that makes it strong. It makes it fast. I'll put fast and strong here so you have both in the notes. Remember, type worksheet, you'll get the worksheet on the notes. Because it wants to attack, it's not waiting around for a carbocation. If there is a leaving group and that leaving group is taking its time, just kicks it out and it's gone. But if the molecule is stable, if the nucleophile specifically is stable, then it's weak. It has no motivation to attack. Why would it want to attack if it's perfectly happy with where it is? If it happens to see a carbocation that happened to take its time and finally form, then yeah, it's going to go and take the opportunity to attack, but otherwise it's just slow and weak and minding its own business. So if it's stable and weak, that will give me a slow reaction. If it's a slow reaction, that's my SN1 reaction. If it's a fast reaction, that's my SN2. And if you watch my other videos, especially where I compare the two reactions, I call them a 1 type, meaning an SN1 or E1, and a 2 type, meaning an SN2 or E2. So the 2 type is a strong attacker, fast. The 1 type is a weak attacker and slow. Make sure you don't just memorize this. Make sure you truly, truly understand what and why behind this so that you can take tricky ones and actually figure out what to do. The next thing that we're going to look at, number 3, is the solvent. So we already looked at the 2 types of solvents where we said that for an SN1 reaction, we have a polar protic solvent. Protic is something capable of hydrogen bonding. So for example, water, alcohol, ammonia, and amine. Actually, ammonia can sometimes do SN2, so you have to look at the conditions. For an SN2 reaction, we have a polar aprotic solvent. And that's what we just looked at on the previous page. An aprotic solvent does not have that protic proton. So DMSO, DMF, acetonitrile, all of that. The idea with a protic solvent, and this is really critical, meaning why does this matter? The protic solvent can stabilize the carbocation intermediates. And remember what I told you earlier. If the carbocation intermediate or any intermediate will be stable, it will form faster. If I cannot stabilize an intermediate, it's not going to form, and therefore the reaction is not going to happen. And the last thing we look at, which is not really a difference, it's more, whoops, where did it go? It's more about confirming that, yes, the reaction can take place, is the leaving group. And what you have to look at with the leaving group, I do not ever, ever want to see you kicking out a carbon. Can it leave? Is the leaving group stable enough? And typically what I'm looking at with a good leaving group are halogens, positively charged molecules, for example, positive charge that will leave and give me something neutral to give me something stable. And I'll show you an example of this. Never kick out a carbon, never kick out something that is going to be really, really strong, like an OH leaving group to turn it into an OH minus. Very, very strong. Do not do that. If you have any questions on the differences, go ahead and type it in. Otherwise, we'll look at a couple of practice problems together. Question, can you talk about the polarizability of a nucleophile? Yes. So let's do an example with that so you can see what we're talking about. If I have something like CH3Br and I choose to react it with sodium ethoxide. So you can see it written like this. You're probably more likely to see it written like this, where the O minus is balanced by that Na. Typically, we're not going to see really, well, actually, you are going to see some really, really strong negatives. But once you get to the difference between SN and E, you're going to have to choose between your nucleophile and your base. In a situation like this, the ethoxide has resonance. I drew it like this, where the negative charge sits at the bottom right. But this molecule can resonate. I can have these electrons going up, that pi bond being kicked up onto that oxygen. And then my other resonance contributor, I don't know why that broke, looks like this, with a new bond right here. And now an extra lone pair from this bond sitting right here on the molecule with a negative charge. So these are my two resonance contributors. This molecule has a negative charge. It is technically strong, but it does not make a very good base. It makes a very good nucleophile. Why does this make a very good nucleophile? In solution, in reality, we don't have this version or this version. We have the resonance hybrid, that intermediate, which has each oxygen single bound and that pi bond back and forth between them, where there is partial negative. Let me make sure the electrons stand out. There is partial negative sitting on this oxygen and partial negative here. It's going back and forth between them. This is a topic you should have learned in resonance. But then, if I bring it next to my CH3Br, where I have bromine, the greedy bastard, pulling and pulling and pulling on the electrons, making carbon very partially positive and therefore susceptible to attack. In the presence of this partial positive, all the electron density is now going to flow towards the part of the molecule that is closest to that CH3, closest to that partial positive charge, and it will polarize. Polarize meaning I have two poles, and I get polarity being drawn to one side of the molecule. That polarity makes this temporarily way more negative, so I get this version of the molecule, and that is going to attack. And you're going to see the idea of polarizability on not just something with resonance, you'll also see it on halogens. Halogens, I mentioned earlier, make very good, very bad bases, but they can be decent nucleophiles. Why is that? If I have a negative charge on bromine, that negative charge is distributed around and around, just flowing everywhere. But if I bring that bromine near something positive or partially positive, all the negativity will flow in this direction. It will bring it all to concentrate on one side and polarize. And the way I want you to imagine this is, imagine there's a school bus with a lot of kids. Some kids are sitting on the right, some kids are sitting on the left, and the school bus is driving. And all of a sudden someone goes, "Hey, there's a unicorn." All the kids will now rush to one side, so that there's no one left on this side of the bus. Everyone is on this side of the bus. And if those kids are the negativity, the concentration of negativity, it is now all concentrated in that one direction. They're all trying to see the unicorn, or in this case, all trying to see that positive charge. That's the idea of polarizability. I know a couple of students asked about that. Let me know if that is clear. Let me know if that makes sense. Is the resonance good for nucleophiles? Yes, because it helps stabilize the charge when the molecule is not reactive. Bring the unicorn nearby, bring the positive charge, and everyone rushes to the side of the positive, and that's when it attacks. All right, let's keep the questions relevant specifically to today's topic. How do we know if the reaction is SN1 or SN2 if we're given a reaction? That is a great question. We look at the alkyl halide. Can I form a stable carbocation for SN1? Is it hindered, meaning to block SN2? Is the nucleophile strong or weak? If it is strong, more likely to go SN2. If it is weak, more likely to go SN1. Is the solvent polar protic? Can I stabilize the SN1 carbocation? Or is it polar aprotic to make the nucleophile more angry and stronger for an SN2 reaction? And of course, do I have a good leaving group? So let's take a look at a reaction that puts this into practice. Say I have a molecule that looks like this with an OH, and this is achiral because I have symmetry in the molecule, so I'm not worried about stereochemistry. And I react this with a solution of HBr. So let's look at it one step at a time. The first thing I said to look at is your alkyl halide. Can I form a carbocation? Well, the OH is sitting on a secondary carbon. That means, yes, I can form a carbocation, but yes, I can also kick it out in an SN2 reaction. The next thing I'm going to look at is the attacker. Is it strong or weak? I didn't give you a solvent. So what is the attacker? Well, let's assume it's a solvent that is not very reactive. And sometimes your professors will not give you a solvent because this is all they want you to look at. I seem to have no solvent until I realize, wait a minute. HBr is really just an H plus and a Br minus. It can separate. And if it separates, my Br minus, it could be a good attacker depending on the situation. My solvent is not given, so we're going to ignore the solvent. Your professors will often skip that. And then my leaving group, well, nothing's happening. That OH is not going to leave. You're not going to have an OH minus unless if your leaving group does not want to leave, how do I make it leave? What is a good way to get rid of something that doesn't want to leave? You beg, you plead, and you bribe it. One way to bribe a leaving group is to protonate it. The oxygen will reach for that proton. And now, when I have an OH2 plus on the molecule, remember when I talked about leaving groups, I said that positive charge going to neutral is something we're looking for. If I have an OH2 plus, that's a positive charge. Now this thing is happy to leave because if it breaks away, then what I'm left with is, well, first of all, a carbocation and then a water molecule in solution. Now, if you remember earlier, we used a water molecule, a solution with Br minus and water, and we said that the Br minus was hiding, it was caged, it was not reactive. Now I'm showing you the same thing with the Br minus in solution. The difference is, in this case, it's not a solution of water, it's one water molecule that just popped off and came off on its own. But I have enough Br minus compared to the water molecule. Now it's in a 1-to-1 ratio. And so now the Br minus can, in fact, come in and attack. And that gives me my reaction. So this particular case was an SN1 reaction. And the reason I know it was an SN1 reaction was very simple. That right there is my carbocation intermediate. If I have a carbocation intermediate, there is no possibility for SN2. It has to be SN1. I see a question, is this going to be posted? For a copy of my session notes along with a worksheet that is not posted on my website, just put worksheet in the comments and I will link you after so you will be able to download it all. So just type worksheet. Even if you're watching the recording, just put worksheet and I will come back days, months, years after. I do try to check through all the old comments and I will catch that and link you. Question. So every time you need to make a stubborn leaving group via protonation, it's not just this one. You have a couple of different options. So I have a video on this where I talk about a tosylate, a methylate, a triflate. So there's a lot of different ones. The common ones you're going to see are SOCl2, a tosyl chloride, a tosylate and a methylate are very similar, and I cover that in a separate video as well. And it's linked in the series in this description. All right, so let's take a look at another one. And for this one, I want to remind you that anytime you learn a trick, don't blindly apply the trick. I want you to pay attention and make sure that what you're looking at makes sense. If I give you a situation like this, and I tell you to react it with H2SO4 in ETOH, ethanol. Don't just jump right to the reaction, to the product where I showed you. You cross this out, you copy it over, and you put the OET on there because you want to consider what is going on. So first, let's figure out what reaction it is. I see that I'm dealing with H2SO4. I know that that is an H plus acid catalyst in solution. And that means I'm not going the SN2 route. You're not going to have a strong attacker with an acid catalyst. That is your clue that you're going the SN1 route rather than SN2. SN1 means carbocation, and this is where I want you to pay attention. If I redraw the skeleton exactly as I see it, and then I consider where I'm going to put my incoming group, remember the backpack trick, cross this out, and I would get an OET here. This is actually not the right answer because we have a carbocation intermediate. And here's a trick I want you to recognize. Anytime you have a secondary position, which is going to give you a secondary carbocation, near a tertiary carbon, I don't know why I put carbocation in there, near tertiary carbon, you're going to get a hydride shift. You're going to get a carbocation rearrangement so that the intermediate for this reaction will actually look like this. And as soon as you recognize SN1 reaction will form a secondary carbocation near a tertiary carbon, now I can redraw my skeleton. This is no longer going to be chiral because once you have a carbocation, it's sp2. And then the incoming nucleophile goes on the unexpected tertiary position to give me the final product. Allie, perfect timing on your question. This right here is carbocation rearrangement. And in the carbocation tutorial linked in the description, I also talk about rearrangement. So make sure you watch the video in that link. If your professor wants you to find the original from the final, let's see. Let me see some thumbs up in the comments if you want to see a shortcut on how to reverse all of these reactions to easily find the original. Oh, there's a delay. I'm not seeing any thumbs up. Oh, there we go. All right. To find the original from the product is very simple. It doesn't even matter if it was an SN1 or SN2 reaction when you're reversing it, because the trick is exactly the same. So let me start with a simple one, and I'll show you a couple. If I have a product that looks like this, and I know I reacted with H2SO4 and H2O, all you do to find the starting molecule is redraw the carbon skeleton and do exactly what we did before. So step one before was the skeleton. Step two was to cross out the halogen. And step three was to add the nucleophile. So here you want to X out the nucleophile, and the way you identify the nucleophile is the thing that is now attached to your parent chain. Cross that out. Step 3 was our old step 2. You want to draw in the leaving group, and if you don't know what it is, just give it a halogen, give it a chlorine, give it a bromine, and all I have to do is this. This was SN1, but it could have just as well been SN2 without the H2SO4. It could have been NaOH or whatever. And so if this was NaOH in DMSO, same exact thing. So let's go back and see how we would reverse the other ones. For something like this, if you reverse it, you will get your halogen here because you don't know where it started for a carbocation intermediate, and your professor, carbocation rearrangement, your professor's not going to trick you like that. Or your professor will say this started with a secondary, they'll give you some kind of verbal clue, but the reversing is the same. For something like this, we identify the molecule, redraw the skeleton right there, cross out, wait, hold on. What am I showing here? Oh, yeah. Cross out the incoming leaving group, the incoming nucleophile, and add a leaving group, which in this case is a little bit tricky because it's OH. But how would you have known that? You would have had to have some kind of clue if it was an OH rather than a halogen. Let's go back one more. Let's see. This one right here, same thing. Redraw the skeleton. Cross out your nucleophile, add a leaving group. If the nucleophile is on dashes, that means the leaving group was on a wedge. So with an SN2, do make sure you reverse the chirality. Question, does the OET product have an enantiomer? OET product, that was this one. In this case, no. Because the product is achiral due to the fact that there is symmetry going down the middle. Now, if I had something else going on here, then yes, I would have had racemic because the carbocation intermediate is sp2 hybridized. Question. In the study hall that you offer, are the videos you offer different from the ones on your YouTube page? Yes. So that is a very good question, Jenny, and thank you for bringing that up. What I have on YouTube here is just, I cover some topics here, some topics there. But if you're looking to work with me more closely, more one-on-one, I have an entire video library on everything Organic Chemistry 1 and Organic Chemistry 2. This includes tutorials, kind of like this, where I teach a topic. This includes practice sessions where we just go hardcore on all the different topics. This includes video solutions to all of the quizzes that I have for free on my website. So any quiz that has PDF solutions, in the study hall, you have that step-by-step video where I actually work through it with you. And the study hall also has a community where you can work alongside myself, my TAs, and other organic chemistry students. And that means you can post daily questions because the videos will teach you and walk you through concepts. But if you have a question on something specific that is not covered in a video, in the study hall, you get to post your questions and you get to have not just an answer. I'm not going to just solve your quizzes for you. Rather, I'm going to ask you, how are you, where are you stuck? How are you trying to solve it? Where is it that you're not sure how to, trying to figure out how to say this. What is the next step that you're not seeing? And that is what I will guide you on. So for more information on the study hall, make sure to go to leahforsyth.com/join.